So we talked about using forces, torques, and looking for the acceleration to figure out how fast something's going. And then we did the energy way as well. We did that with a hoop on our last example, if that's a video you just watched. Well, I want to explore this topic just a little bit more to solidify it and lock it in. So we're looking at example 1 today. It's a rod that's free to rotate. So we have here is we have not an axis rotation, we have a point of rotation, and the length of the rod, I kind of extended it too much here. The length of the rod is just from here to there. And this is free to rotate. So it's starting off horizontally, and it's starting from rest, and it's going to rotate down to some position at the bottom there. And what we're going to solve for, we're going to solve for the initial angular acceleration alpha and the initial linear acceleration a, just as that rod starts to fall. Some givens, they're going to tell you, hey, the length of the rod is L, super helpful, right? It's got a mass M. It's starting from rest, so V naught and omega naught are 0. Oh, that's a typo. I should say radians per second, rads per second. Rads, because it's angular velocity. And the moment of inertia of a rod fixed around the left endpoint or right endpoint is ml squared over 3. So they'll give you some things like that. On the AP test, they don't always make you memorize stuff like that, and if they do, they might make you derive it, which we've practiced, and we're going to practice more. So you're given that, and they want you to figure out, hey, can you figure out what the initial angular acceleration is here, and can you figure out the initial acceleration? Once you get the alpha, it's very easy to find the linear acceleration of the A, because they're related in a simple fashion. So one little thing, I say the phrase initial here because there's going to be a certain torque on this beam that causes it to move. But as that beam moves, the angle between that force vector and the R is going to change. So the torque's going to change, which means the angular acceleration is also going to change. So I'm just saying that just initially when this beam starts to move, we're looking for that angular acceleration. All right, so step 1, we're going to practice using torques and forces to look at it here, but actually we're going to practice using torques right here. So step 1, we draw a picture. And there's our beam right there. It's got length L. And step 2, we put our force in there. The only force bringing this beam, or causing this beam, the only force causing this beam to rotate is the force of gravity. If this is L, the force of gravity, if it's a uniform board or beam, happens at L over 2. And that's it, no friction. But keep in mind, net torques lead to net acceleration. So remember, net forces used to lead to net accelerations, the delta V's equal delta X's. Now we're just doing the same kind of thinking process. Net torques lead to angular accelerations, lead to delta omega is equal to delta theta. So you're not relearning all new physics. You're just taking all that good physics you know and you're applying it to rotational concepts. So we have this force, and so we say, hey, we have a force acting at a certain lever arm here, so that's a pretty good indication that we're going to have to use torques to solve this question to get this. Now, step 1, we drew a picture. Step 2, we label our forces. Step 3, just a normal coordinate system, but because it's a torque problem, because we know it's going to rotate, we have to pick our point of rotation. Makes sense to put it right next to the hinge there. I always put a star next to where the point of rotation is, because that reminds me that's my 0 point right there. So the torque, force of gravity, it's acting at a certain R, sine of theta. Remember, there's your lever arm right there, and the force of gravity is going down. So that's a 90-degree angle between your lever arm and your force. So that's going to be 90, sine of 90 is 1. Okay? And remember, Newton said F equals ma. In this case, we're not talking forces and acceleration. The analog to that is torque. Net torque equals I alpha. So they told us the I, it's over there, ml squared over 3. Alpha is the angular acceleration, so you're feeling pretty good. Fug equals mug. Force gravity is mass times gravity. Here's what trips some people up. The lever arm R is not L because gravity is not acting here or here. Gravity is acting at the center of mass of the object right in the middle, which is L over 2. So that's your lever arm. We already reasoned through the sine of 90, which is going to be 1. And this works out pretty slick. So we plug in mg right there. L over 2 simplifies there. The I equals ml squared over 3. We rearrange things, and we get alpha equals 3g over 2L. So that is really important. That's just as it starts to move, because that's the torque just as it starts to move. But as this beam starts to move, you can almost picture like that angle. There's your R, there's your FG. That angle between those two vectors is going to change. So your torque's not going to be the same, which means your alpha is not going to be the same. So that's your initial alpha as it starts to move. So alpha is not constant throughout the rest of the process. It's going to be changing because the angles will be changing. Because you can picture the extreme situation when the beam's directly downward, that you have force gravity going down and the radius going down in that direction, so you have no torque in that situation. So now here's the deal. If you don't have these down, S equals R theta, derivative of that's velocity, derivative of that's acceleration, derivative of that's omega, derivative of that's angular acceleration. So we're just going to relate this right here. We know with alpha, if we times it by the R, that gives us our tangential acceleration, or A, our linear acceleration, however you want to call it. So we're just going to make that little substitution. Angular acceleration equals A2 over R. So over here, we're saying, all right, we're going to solve for part B right here. we use AT over L, which I said L because that's the length, so the length of our rod right there. So we do that, and you cancel some things off. Your L's go bye-bye, and you get 3G over 2. So the really important thing, this is the linear acceleration right at the end point right there, because I said R right there was equal to the length of the rod. So that's why R equals L when I did a little substitution. So that's a little setup right there. I think that's a lot more reasonable kind of situation. And the big thing I want you to realize is if you have a greater torque, that's going to lead to a greater angular acceleration. That's the big idea right there. Let's take a look at example 2. We're going to use torques again. So example 2, the setup is you're going to have, picture like a hoop, and you're going to have a pulley and a string. And this is a little kind of complicated actually, but it's fun. So you're given a hoop. The moment of inertia of a hoop is mr squared because the mass is right around the outside perimeter of the hoop. And at the same time, so you have a hoop and you have a block of mass, little m right here with a rope, and it's attached to the hoop. So you're like, whoa. And you can almost picture this. This hoop would want to rotate, and then you put a string on there, and that string's going to be connected. And so as this block falls, can you picture that's going to apply a force right there? That force is pulling down. It's going to cause a force at a radius, which is a torque on this hoop, and it's going to cause that hoop to rotate. So the big thing is you have this setup right there. We're going to solve for the initial angular acceleration of the hoop, and then eventually the linear acceleration AT at that point. Okay, but the big picture is kind of weird. They could say it's a pulley or whatever, but this question gets super complicated if you don't know the moment of inertia. So I just picked as a hoop because I do a moment of inertia of a hoop is mr squared. If you ever get stumped on the AP test and you don't know the moment of inertia, but you need that for the rest of the problem, you could say, I'm going to assume the moment of inertia is this, and go with it, and then do all the good physics, or just call it capital I for moment of inertia. But you have a mass, little m, attached to a hoop, mass, big M, causing it to rotate. I tend to mess up little m's and big M's, but this is little m. This is going to be the mass, big M. And you might want to call them 1 and 2, if that helps you out. So, all right. We know we're going to have to use torques because we know as soon as we release this, say our hand was holding that block right there, as soon as we release it, there's going to be tension in the cable. The tension is going to put a force tangent to the circle here, which is going to cause us to rotate. That's a pretty good indication of using torques. So we sum our torques. And keep in mind, step 1, we drew a picture. Step 2, let's label our forces. So if we're looking at from the block's perspective, this block has the force of gravity, little m, fug, little m times g, and playing up on this block is ft. And I should actually make this vector longer because we know it's going to cause it to rotate. So this one's going to win over the tension vector there. So we have that. And so we're saying, hey, this tension is connected right here. Now I know this is weird. When we sum our forces, we did it relative to that block right there. And I said ft's up, mg's going down. But now when we look right here, this disc just wants to hang up. There's a rope attached right there. And I shouldn't say disc, it's a hoop. So from the hoop's perspective, this ft is pulling right there, and that's what's causing the torque. So when we go to sum our torques, the reason this hoop is going to rotate is because there's a force applied at a certain lever arm away from this point of rotation there, causing a torque. So a force at a radius is a torque. So we have that, a force at a radius, and I put a negative here because this is going to rotate clockwise, which is a negative torque, okay? And F equals ma is our, we used to do it in Newton's laws, so torque equals I alpha. And I also put a negative right here because this wheel is rotating clockwise. That is a negative angular acceleration. And I was being kind of thorough because the negatives will go bye-bye anyway, but I just wanted to be thorough, okay? That is the only torque acting on our hoop system right there. So we are done with that. And you simplify it down here, and you get Ft times R equals I alpha. Remember, I reasoned out this is a 90-degree angle, sine of 90. Right there is 1, so it's maximum torque. And you get angular acceleration as force tension times R over moment of inertia. Now real quick, I love questions like this because yeah, you get caught up in the details, but doesn't this just kind of make sense? If you have a greater force tension, so the side of the equation gets bigger, that means you have a greater angular acceleration. If you have a greater moment of inertia, so like it doesn't really want to move at all, because remember moment of inertia, it's about the mass and how it's distributed, but if I gets big, if you divide by a big number, that means you're not going to have a very high angular acceleration over here because the hoop doesn't want to rotate. So just something to keep in mind. This just makes sense. Our logic makes sense. So yeah, there's some math here, but the logic of the physical situation makes sense. All right? So the bummer is we're looking for alpha. We don't know ft. So we got to come over here and explore a little bit about ft. So if you're like, I'm tired, this is tough enough. If today you understand where this came from, that's a really good start. All right? But let's go look at ft. You know how to do this. We've done this a whole bunch. you have forces acting on an object. You sum your forces, not in the x. We're going to sum it in the y. That's what we're going to do right now. And one little thing here. Oh, I kind of defined my coordinate systems. I said positive was in the downward direction. If you want to do it differently than that, I said, oh, I'm going to go in the direction of motion here. X is to the left there. So negative ft plus mg, because it's moving in the direction of my positive y-axis there, equals may. I think I did that just because I knew my net acceleration would be positive and in the downward direction. So here's the deal. You're going to solve it for ft. You get ft equals mg minus may. And then once you know that, we know m, it's just lowercase m, we know g, we know this right here. Now the bummer is the same problem we run into. We get this equation that has an ay or at, whatever you want to call it. It's some, you can call it at or ay, it's just some linear acceleration. But we had alpha up here. So the deal is this, you got to remember this. Yeah, I did a little step here. I said, hey, you can call it AY or AT. It's just some linear acceleration. And so you get this right. You're like, oh, it's the same situation we run into. We don't know alpha. We don't know FT. We don't know FT. And now we introduced a new variable. So I'm just going to take a moment here. We're going to say, hey, don't forget that A equals R alpha. And that comes from S equals R theta, which comes from V equals R omega, if you want to keep writing that down. So instead of writing down acceleration, I'm just going to call that R times alpha, and that's going to make life easier. So it might make a mental note here. If you want to relate like your linear acceleration, I'm being a little lazy. Whenever you see little a like that, that's just your linear acceleration. And we're going to say that your AY equals your AT at that point, because we're going to say, hey, well, however much this accelerates, we're going to say there's no slipping here. It's not like this is going to start to go before the wheel starts to go. We're just going to say it's dropping down there, and it's causing that wheel to rotate instantaneously without slipping. So we have right here, we're going to say, hey, that's just R alpha. We're going to put 1 and 2 together right now. Equation number 1, and I've started numbering my equations because as we get into these really heavy-duty physics ones, equation 1, that's huge, big physics idea, torque. This one we use forces, so we have equations 1 and 2 we're to work with. So equation 1, we have FTR over moment of inertia. And we say, hey, you know what? We know the moment of inertia of a hoop, it's mr squared. If you didn't know it, make it up and say, I'm going to assume it's this, but of a hoop, we know it's mr squared. And then we're like, okay, that makes us feel good. We got to get the tension out of there, so that's where we're going to hang out with equation 2 here. And I had an r over an r squared, so I canceled the r on top and reduced that power. And you're like, all right, let's get the ft in there. Well, we know ft equals mg, little mg minus little m times at, but at equals r alpha. I'm going to do that substitution right now. And I was a little lazy. This should be a capital R. It's the whole radius of the hoop right there. So we have this right here. We have mg minus mr alpha over this. And now the goal is alpha equals this mess right here. And you do some algebra, rearrange it, and you get something like this. Boom, boom, boom. You factor the alpha out right there. You divide through, and you get something like that. Now, just to be very clear, this is little m. This is a little m, and that's a capital M. So I'm really sorry that my m's kind of messy there. So we have that right. That's your angular acceleration. If you have a really big radius on your solid hoop there, so divided by a big R, it's not going to accelerate as well because it's going to have a larger moment of inertia, so it's not going to really want to angularly accelerate very much. And one last little thing, they said, hey, once you know the alpha, can you find what your AT is? So instead of doing angular like radians per second squared, can we get meters per second squared? And just remember that relationship, AT equals R alpha. So if this is your alpha right here, you just times it by the R, and that'll get you to the linear acceleration there. Times this by R, and then you'll realize you have an R on top and bottom. It just simplifies down to little mg over big M plus little m. That's just something to watch. And that once again makes sense because if you had a block, that little m, let's say that there's a very massive block, you times it by g, then it's going to have a larger linear acceleration there. And that makes sense. Yeah, I know it's on the bottom as well, but you're times that little m by gravity on top there. And once again, if you have a very, very heavy disk, so you're dividing by a big M right there, well, then all of a sudden your linear acceleration is not going to be very large at all. So that is very difficult. I will say that's about as tough as the questions get all year. Using torque and forces and doing that, relating linear to angular acceleration, that's about as tough as it gets all year in my opinion. We're going to finish by doing a little energy example. So thanks for watching.